So welcome to the next webinar on modern Java by example. What we're going to do today is we're going to talk about some other RxJava examples. And if we have time, we'll also go back and revisit the example I gave from a couple days ago using RxJava. I've come up with some more clever ways to improve the performance of the RxJava example. And actually, we'll get a chance to show a couple of different variants of that here in a minute. But first, let's go ahead and talk about what we'll be covering today. Let me share my screen, and we will start off by going over here, and we'll go to the GitHub account that we'll be covering. So if you go here to GitHub, and you take a look in the RxJava folder, you'll find something called EX3. And that's what we're going to start out with today. We will cover other things later as we have time, but that's what I want to start with today. Okay, so with that as a starting point, let's go ahead and jump in here real quick. All right. So let's go over to my IntelliJ project. And here you can see that we have the EX3 project open. And let's go ahead and take a look at it real quick. So this particular example is going to demonstrate a bunch of different RxJava mechanisms for determining if a flow of random big integers are prime numbers or not. And so I'll talk more about that when we talk about the actual design of the program. You can imagine you would have some kind of feed of information. Maybe it's stock prices or something that has values that are changing over time. And we want to do something to every element in that feed. That's kind of a classic RxJava style application. We're going to show a sequential flow, what was largely sequential, now it's completely sequential. And then we'll also show two different ways of using concurrent flows in RxJava. And this example will also illustrate the use of a memoizer, which is a data structure that's based on Java's concurrent hash map, which allows us to be able to cache the values of checking if the numbers are prime. So this is a cool technique that I think you'll enjoy looking at. So let's go ahead and look down here. You'll see that we're going to have a range of values, and they're going to be within a certain range, but they're going to be large numbers, so it could take a while to check whether they're prime or not. We're going to have a cache, which we call M prime cache, and we use that as a memoizer. And the memoizer is basically going to check to see if the value is already in the cache, and if so, it'll return it. Otherwise, it'll call a function, which will compute the result, which in this case will be a check whether or not something is prime, and then it'll enter that value into the cache and return that value, keeping it around for subsequent uses. For the test program, we're just going to run 10 iterations of this stuff. Of course, in real life, you would have a real live feed that could go on forever. And we're going to have a little duration. We're going to say we're going to get new samples every 100 milliseconds. So basically 10 times a second. And then I also define something called a scheduler, which is used by RxJava to determine where to run the computations on that are doing the processing for the samples that are flowing through it. Okay, so you'll see that we're going to have three different tests. First, we're going to start out with test sequential. Then we're going to do test concurrent observable. And then we're going to do test concurrent flowable. So without further ado, let's just go ahead and run this program. And you'll see this is this entirely sequential version. And so what it's going to do is it's going to come down here, and it's going to go ahead and emit a bunch of numbers. And you can see that these numbers are within a range. And I chose the range carefully, as we'll see shortly, to ensure that we have duplicates in this range. So I emit all these numbers, and then I go and check whether some of the numbers are prime. You'll notice that wherever we have a duplicate, for example, there's 92 as one of the duplicates, because it also occurs up here. And let's see, I think 97 also occurs. You'll notice that down here, when we check to see if a number is prime, we never check duplicates. And that's because we're going to use the memoizer to remember the result, and it'll simply return it. And then the final thing that we do in the main thread is we go ahead and indicate which of these numbers are prime numbers. And if something comes back as, actually some of these things, whoops, they should be giving different results in some of these cases, but we'll look at that in a second. So this is basically what's going on for the program. So let's pop back over here for a second and take a look at test sequential. So test sequential is going to go ahead and set the scheduler to be the so-called trampoline scheduler. And as you saw when I ran the program, the trampoline scheduler ensures that everything runs in the main thread. That's the main thing we're trying to do here. So once we've done that, then we go ahead and we create a flow of observables, and we're going to use the Omit factory method, and it's going to create a flow of random big integers within that range to ensure duplicates. And we'll come back in a second, and we'll talk about how this all works. We're then going to go ahead and check to see if the number is prime or not, which is going to use our memoizers. We'll see in a second. And notice how this is using the map call. Map is very much like map in Java streams. It transforms its input stream and returns something that's been transformed. And in this case, we're going to take a big integer in and return something called a prime result. And then what we do is we go ahead and use blocking subscribe. And I'll talk more about blocking subscribe later and what the implications of using blocking subscribe are. And what we're going to do is for every normal result, in other words, not done and not error, we're going to go ahead and call this method reference. So for those of you who are familiar with Java streams, this should look very familiar, except we're working with observables, not with streams. So let's go ahead and take a look at the omit method, because that's a good one to start with. So let's go down a couple of calls here. So here's the omit method. The omit method is one of many, many, many factory methods that RxJava has. So RxJava in this case is using the create factory method together with this omit method. And the omit method is passed an emitter, and the emitter is used to be able to emit samples or data that are going to then flow through the rest of the observable flow. Let's call it the stream, for lack of a better term. So the particular example we're going to look at here is intentionally designed for this incarnation to be done in a single thread. So what it's going to do is it's going to figure out the origin point for the random numbers, which is the big value minus the number of iterations. And that way we're going to increase the chances that we have duplicates in this range. We create a random number generator, and then we use a method on observable called interval. An interval will generate a flow of longs every duration, and the duration here is 100, so it's every 100 milliseconds a long will be emitted. Now, in this particular case, the long is just 1, 2, 3, 4, 5, and so on, and we're going to completely ignore the values. We're just going to use that to kind of be a pulse. So this is mimicking connecting our program to some kind of input device, like a network socket or something like that. And the scheduler here ensures that everything runs in the main thread. Now, by default, if we were to omit the scheduler, it would run on the computation scheduler, which runs in a pool of threads in the background. And we'll take a look at that later. What we then do is we take the next random integer up to S max iterations, and we add it to the origin. So that'll get us numbers within a range and get duplicates within that range. And they'll be big numbers. Then we take that stream or that flow of random big numbers, and then we go ahead and print them out using a debugging aid. And you can see that if you take a look at the code here, you can see we say we're omitting the number in the main thread. And then we go ahead and only take up to S max iterations of these things. So we're bounding the amount of processing in the stream. Now, of course, if this was a real program connected to a real source of data, it might not be bounded. It might go on forever, or until it crashed or was shut down. And then the last thing we're going to do is we're going to go ahead and do a blocking subscribe. And that's going to block and emit each random number. And blocking subscribe simply means that the call won't return. It'll block the calling thread, and it'll go ahead and block on that thread, and it won't return until basically we've taken all the elements we want to. If we used a regular subscribe, which is more common, then our program would have some issues and we'd have to put timeouts and it would get ugly. So this basically is going to go through and generate up to S max iterations, in this case 10, large random big integers, and it's going to call the onNext method, which is going to push them up the stream. And then when we're all done, we shut down the input stream and say we're complete. So that's a very common way of being able to generate data, and this is what's called a cold observer, and we can talk about that at another time. All right, so let's pop back up here. So that's how we get the data that we're dealing with. So you can see, let's go back up, and we're in test. We're in the test for the sequential version. So we've got a sequential flow of items, and then we're going to run it through check if prime. So now let's go ahead and take a look at check if prime. So check if prime is a little helper method, and what it does is it takes a big integer, which is the prime candidate, and it goes ahead and it will call it'll call the compute if absent method, passing in the prime candidate, which is the key, and a method as the value. And what this method is actually not the value, it's a value generator. It's a generator function or a mapping function. And what it's going to do is it's going to go ahead, this method, compute if absent, is an atomic check then act method that looks up to see if prime candidate is already in the concurrent hash map. And if it is, it just returns the value. If it's not have a value associated with it yet, then it'll call the isPrime method. And then the isPrime method will do its thing, and then the result of that will be stored in the concurrent hash map as the value, and then that value will be returned as the result of compute if absent. So you can see this is essentially acting as a memoizer cache. And you can find out about memoizers by Googling memoizer. It's an interesting data structure. So here's the isPrime method. This basically goes and checks to see whether a number is prime. If it is prime, it'll return 0. If it's factorable, then it will go ahead and return the smallest factor of that number. And so we'll talk more about this method later. So this is basically just checking to see if something's prime. And you can see that what we're doing here is we're putting the result of this into something called a prime result. And the prime result is defined down here as just a tuple that maps the prime candidate with the smallest factor. Okay, so that's the next stop here, is this. And let's go back up to the top, and we'll take a look at what happens next. So the next thing we're going to do is what's going to come out of here will be basically a flow or a stream of prime results. And the blocking subscribe method will then call the process result method if all goes well. So if everything goes through, there's no errors, we're not done, the process result method will be called. And you can see that there's different variants of blocking subscribe. This is the one that also wants to do something in the case of errors or in the case of completion. We could also just do this if we don't care about errors and completion. So this is essentially the normal processing flow. So let's go ahead and take a look here. Go look at process result. And here's what process result does. It goes ahead and checks to see whether or not we found a prime number or not. And I think I got this backwards. So it probably should be if not equals 0. So if it equals 0, that means that we found a prime number. Otherwise, if it does not equal 0, that means that we found something that was a factorable number, and we'll print out the smallest factor for that. Don't worry too much about the processing. I'll go ahead and fix that later and upload the fixed version. So that's what process result does. It takes a prime result, figures out what we got, prints a result. Okay, so that's basically what we've got going on with the sequential version. Now let's go ahead and take a look at a couple of different parallel versions. And these are really quite interesting, and they will show us other interesting facets of RxJava. As you probably know, if you've been following me for a while, I'm a big fan of concurrency and parallelism, so that's my interest in all this stuff. So let's take a look at how we could do this concurrently. And hopefully this will give us sensible results. Okay, so now what you're seeing here is the fact that my algorithm has a bug, but ignore that. What you're seeing now is that unlike before, where it would go ahead and check first to emit all the numbers, then to check them, and then to process the results, now it's going to go ahead and interleave all these things. And that's why, of course, I am printing the results out, showing what thread it comes for. So here you can see that we're going to be emitting the numbers in a computation thread in the computation thread pool. We're going to be checking the numbers also in a thread in the computation thread pool, but it's a different thread. So we've got these things going concurrently. And keep in mind, my laptop has 12 virtual cores, or 6 real cores with hyperthreading. So there's lots of cores out there to do processing on. And then finally, we go ahead and we'll print out the result. And you can see that this will give the result back here. And we can use that result in order to do something with the result. So again, we'll go back and look at this stuff later and make sure it's actually correct. But that's not important right now. I'm looking at the structure, not the way the actual algorithm is working under the hood. So as you can see here, this particular approach is going to process it's going to do the processing of the result in the main thread. And I want you to remember that because I'm about to tweak the program to get it to not process it in the main thread. And you'll be really interested, I think, as to why that's happening. But the main thing I want you to see here is that it's interleaving all of these different computations. And that's important. So let me go back over here and let's take a look at test concurrent observable. And we'll see what does it do and why it does what it does. So this is kind of cool. It's going to use the same emitter as before. So if you recall, before we had an emitter that was going to generate data at a certain rate. In this case, we're using the default. We're actually using the computation scheduler for the interval method, which is the default behavior. And so that will then emit in a background thread. We're then going to call the subscribe on method. Now, there's a couple of methods you can use in RxJava to get things to run concurrently or asynchronously. And they're a little bit mysterious at first, for sure. So let me explain them if I can. So subscribe on basically says everything before this method is called and everything after this method will run in a thread from this pool or threads in this pool. In this case, it's the computation pool. There's a couple of predefined pools like computation pool and IO pool. You can set it from your own pool using the from method. There's the trampoline that tries to run it in the current thread, and so on and so forth. So this will make sure that the computations here run in another thread in the computation pool. So as a result, checkif prime is going to be running, as you can see here, in a background thread from the computation pool. Well, something funky is happening, though. The main thread is being used to process the result. Why is that? Well, the reason is because I used blocking subscribe. And blocking subscribe basically is like a barrier synchronizer that will simply do all the final processing in the calling thread, which in this case is the main thread. And therefore, we don't actually have everything running concurrently in different threads. So let's fix that by just changing blocking subscribe to subscribe. And now let's go ahead and put a little sleep here. And you'll see this is one of the kind of quirks of RxJava. You've got to figure out what to do with asynchronous processing because subscribe will not wait. It'll just go ahead and do its thing. So if we don't put a sleep here, it'll fall off and go off and do other things, and the program will shut down, which is not what we want in this case. So I use a little sleep here. So let's rerun the program. And you'll see what we get this time is that even the computations that are looking for or actually printing the results out, they are now running in background threads as well. So we're emitting in background threads, we are checking in background threads, and we're also then printing the results in a background thread. And you can see that those kind of alternate back and forth depending on what's available and what's busy and so on in the computation pool. You don't really have a lot of control over the way that the pool works, but it'll do a smart thing on your behalf. So now everything's running completely concurrently. So we're emitting concurrently, we're checking concurrently, and we're printing the results concurrently as well. And that's all because we changed from using the blocking subscribe call to the subscribe call. And therefore, since we did the subscribe on method here, that means that the map will be done concurrently and subscribe, and the results will also be done concurrently as well, all sharing that particular pool. So that's pretty cool. All right, let's go ahead and set it back to where it was before. And then let's go ahead and run the third method. This is a sort of a newer set of capabilities. The subscribe on technique's been around for a while. This method is going to be using something called a parallel flowable, and that's a newer mechanism. I think it came out in RxJava 2, perhaps. So let's go ahead and run this result, and I think you'll see some interesting output here. So what you'll see here is that we're emitting in background threads, we're checking in background threads, and you can also see if you look carefully at the input here, or rather the output here, where we're using our cache to avoid actually having to check and see whether something is prime, because we've already computed whether it's prime or not. So in these cases, for example, you can see that the value 92 appears multiple times, and the value 99 appears multiple times, but you'll only see one call to checking if for each of those things. So you'll only see one call to checking if for checking if 99 is prime. You'll only see one call for 92 is prime, which you see here, because it's being cached by the memoizer in the concurrent hash map. But now something funky is happening. All the output is being processed, or being printed, I guess is a better term, because we're not doing very much processing. All the output is being processed in the main thread, and it's all being done at the very end. So it's basically doing kind of a fork join-like model where we fork everything off, everything runs in parallel, and then we join and we print all the results sequentially. So let's go ahead and take a look and see what that code looks like. So we'll go look at test concurrent flowable. And here is test concurrent flowable. If you looked at the observable one, we use the observable class to create and start everything in motion. Down here, we're going to use the flowable class instead. And flowable was added later in RxJava in order to be able to handle so-called back pressure, in order to be able to queue things up and buffer it. I'm not going to talk about buffering today, because this example doesn't really lend itself to it. But if you had processing that took a long time to run, you might need to buffer it. And so here we're going to be able to buffer things. And there's other options besides buffering. You can drop, you can keep the last items, and so on and so forth. So in this case, we're going to be emitting things concurrently as before with our emitter. That's unchanged. But as soon as we get the stream of random big integers to come out of the emitter, we're going to convert this to parallel processing. This is a lot like parallel streams. So you say dot parallel here, and that creates, as you can see, a parallel flowable. So now everything's going to run in parallel. And we're going to go ahead and run the parallel computations on the computation thread pool, which is the same one that's being used by the emitter. We could easily change this to use the IO pool. In fact, let's go ahead and do that just for kicks, and let's run this, and let's see what the results look like. So you can see here, now when we do this, we're emitting on the computation thread pool, but we're doing the checking on a different pool. So this is the IO pool as opposed to the computation pool. And you can see how absolutely trivial it is to switch back and forth with these different pools. So it doesn't really matter, because this is not an IO bound job. So we could do it on computation, we could do it on IO. We could also say from fork join pool common pool. So that would be another thing we could do. Let's just for kicks, let's go ahead and run it now. And you should see that the checking is being done in the fork join pool. So take a look. You can see that it's doing the checking for primality in the fork join common pool. So in the common pool of worker threads. So the point here is you can just change these things to your heart's content. I'm going to go back and leave this with computation just for kicks. So we then go ahead and check if the number's prime, but it's now running in another thread. And then we go ahead and we do a dot sequential call. And dot sequential is kind of like a merge or a combine or a collect or something. It's not really a collect. We'll look at a collect later. But it's basically saying merge those flows back into a single flow. So we're going to merge the parallel flows back into a single flow. And then we go ahead and we do our blocking subscribe. Now, again, in this particular case, we're using blocking subscribe, so everything's going to be done in the main thread. Just for kicks, though, let's see what happens if we go ahead and put a sleep in here for a second. And let's go ahead and change blocking subscribe to subscribe. Let's see what the implication of that is on the output, whether it'll still run on the main thread of control. I think it probably will. Let's see. Oh, no, I take it back. Now that we did that, now it goes ahead and you can see it's going to do these things truly in parallel. So a more effective way of being able to do all this kinds of stuff. And you can see that we get the results coming back in the computation thread pool. So that's what we're ending up using here for this particular computation. So once again, you can see that there's a penalty for using blocking subscribe in terms of reducing the amount of inherent parallelism in the system. And that's okay for the little test programs that I'm doing, because I don't like to put sleeps in them. But if you were doing a real program for production uses, you probably wouldn't do that, and it would be running more as a server, and so you wouldn't have to worry about it having the main program shut down. Okay, so that's basically what I wanted to show you guys. Let's see if there's anything else here interesting to take a look at. I don't think so. There's just a couple of methods that print stuff out, and one that is a helper method that calls sleep. Okay, so that's the first thing I wanted to talk about. Now we're going to talk about some other stuff in a minute, but before I do that, let me go ahead and take some questions, because it looks like we have some questions coming in. Okay, so it says, does the blocking subscribe make sure that the thread blocks until all the items in the stream are processed? Basically, what blocking subscribe is doing is it's just putting a barrier synchronization at that point, and it's going to process all the results that come in, and it won't return from blocking subscribe until everything's been processed. So you can think of it as like a barrier synchronizer. Does the emit make sure that X number of items are generated before calling the next step in the pipeline? So in this particular case, it's just generating them. There's no attempt at back pressure. It's just going to generate them, and they will end up being, I guess, queued up internally, especially when it's done in another thread, which is what you saw when we ran the emitter in its default behavior, which was to run in the computation thread pool. Sequential example, blocking subscribe is called from two places, in emit and the calling function. Why do we have to do this twice? You don't really have to do it twice. I was just showing how we would generate the data. There's all kinds of different ways to emit the data in that particular case. Let's go back, though, and look at the code just to show exactly what the question is. So here we are calling the emitter, and the emitter is intended to not return until it calls done. So that's just the way that emitter works. And you can see here that the emitter is going to, it's basically going into a loop, if you think about it. And it's going to use the interval generator method to generate sort of a heartbeat. So every 100 milliseconds, it'll generate a value, which is, we just use this kind of as a pulse to get things running. I also could have had a for loop here with a sleep statement that would have done pretty much identically the same thing. We're just using this as a way to pulse stuff. An earlier version of this program, I had written it so that it used Java streams instead of using RxJava, but I thought I would redo this. I had Java streams and basically doing the same kind of thing with a Java stream, but I wanted to redo it using an observable just to make it more pure RxJava. So this is the way you're intended to write emitters. So the question on the table is, why do we have blocking subscribe for the emitter? And what I want to do is show you what happens when we don't have blocking subscribe for the emitter. So let's first start by doing the sequential version. And let's go down here and we will convert blocking subscribe to subscribe. And we go ahead and run it. And you'll see what it does now is that it interleaves emitting and checking. Everything's done in the main thread, and it still works. So that's good. Now let's come back over here, however, keep it with subscribe instead of blocking subscribe, and let's come up here and let's change it from the sequential version to the concurrent version and see what happens. And what you can see happens here is that the program just basically doesn't do anything, and that's because it fell off of main. So we've talked before about the dangers of falling off of main. And so what happens if we take blocking subscribe out there, then it's going to go ahead and not do any computations. And that's obviously not what we want. So that's why we left blocking subscribe in. And I think that's kind of weird. I think what's happening there is that the blocking subscribe is making sure that we don't return too quickly from main, which is what's happening when we take out blocking subscribe. So anyway, I hope that explains or shows the difference between blocking subscribe and subscribe. So I put blocking subscribe here to make sure it would work for all the different variants. Does the emit and the computation happen on the same thread? So keep in mind that computation is just a method that returns the appropriate CPU-bound scheduler from RxJava's schedulers utility class. So I'm not sure what you mean by saying, do emit and computation happen on the same thread? The answer is the computation is getting us a pool of threads to use, and then depending on how we've configured the emitter, then it will either use the computations pool, in the case that we use the computations pool, and that's the default if you use interval, or it'll use the trampoline thread, which will be in the main thread. So that forces it all to be completely serialized. Is sequential similar to the flat map operation? Not really, no. It's kind of more like a join operation, or it's really a barrier synchronizer, I think is probably a better way to look at it. Okay, let's see. Since the emitter generates values every 100 milliseconds, in this case, emit generates X items. So the method will only return after 100 times X milliseconds. Yeah, that's right. Let me go back and share my screen again, and you can see it. So let's share this. So you can see that this particular, oops, let me go look for the emit method. The emit method is going to run for this many iterations. Let's say it has S max iterations to run, and it's going to generate data every 100 milliseconds on whatever scheduler it's been given, and it'll take up to the first S max iterations of them, and every time through, it'll go ahead and emit the next element. So it'll keep emitting those things up until S max iterations is hit. So S max iterations times 100 milliseconds, that's how long that method's going to run. And then the last thing it does, as you can see, it shuts the emitter down altogether. Okay, so that is the discussion I wanted to have on the example 3. What I want to do now is I want to go back to the example from the other day. The other day we had done an example that compared and contrast parallel streams and RxJava with respect to downloading files and basically converting them from, turning them into images. So I want to go back over to that example because I've got much cooler ways to show you how to do RxJava concurrent processing now than I had the other day. So let's go back over there. So in this case, we're going to share my screen and go to the EX2 project. So let's go ahead and close this project. Oops, hold on. That killed my, killed something. Let's see, there we go. All right, so now let's go back here and we will share this project. So this is the project we've been looking at the other day, and this is the project where we had demonstrated the use of parallel streams to download images using the common fork join pool with the managed blocker mechanisms or not. And now we're going to look at two new RxJava versions of this that use the appropriate way of doing concurrency. And they're a little bit wacky. You've seen one of them already because it's a variant of that parallel flow code we looked at. But we're going to look at another version. And you'll see it's a little bit more complicated at first glance to get things to run in parallel with RxJava. And I think you'll also see when you look at the comparison with parallel streams is way easier to get things to run in parallel than RxJava. So let's first just take a quick look at the parallel streams version. Here's the parallel streams version of this code. Super simple. We get a list of URLs. We convert that list into a parallel stream. We download and store the images in parallel with that parallel stream, and we collect the results into a list of files, and then we print the results. So very simple. It takes almost no time to read this, and the difference between the sequential version and the parallel version is only a matter of changing parallel stream to stream or vice versa. So pretty much equivalent programming for both. Now let's go ahead and take a look at how you would do a parallel download for RxJava, which turns out not to be the same as how you would do it for sequential RxJava, which is a little bit awkward in my mind. So here's what this looks like. If you take a look here, you can see that we take our URL list and we convert it into a flow of observables. So we have a stream or a flow of observables of URLs. And then we have to call flat map. And that's quite unexpected. This is I would call this an idiom. So for flat map, it's going to take every URL. And then for every URL, it's going to use observable.just to omit that URL. And then it's going to go ahead and use subscribe on to subscribe this particular processing flow in a thread, a worker thread from the common fork join pool. And then we're going to go ahead and apply the download and store image function. So what we're saying here is within the context of flat map, for each of these different flows of just one URL, so we're going to treat each of them separately, those are going to get subscribed to run on the run concurrently or in parallel on the common fork join pool. So basically everything inside of this flat map is going to run in parallel. And then we go ahead and we close the paren here, and then we collect the results into an array list, and then we print the results. So I think you'll agree that this is more complicated than the parallel streams version, which is super duper concise and much easier to understand. And you can go back and forth between sequential and parallel with the snap of a finger, like Thanos from the Avengers movie. Whereas this particular way of doing this processing in RxJava is very idiomatic and idiosyncratic. So it's a little harder to know what you're doing, and you can't easily go back and forth between parallel and sequential. I guess you could change this to be trampoline or something, but it's more awkward. Let's now go look at another way of doing this, and this is the one that uses parallel flowables. So this is a little bit more like the way that it works with Java streams and parallel streams. So in this case, instead of using an observable, we use a flowable. So we get our stream of observables, or in this case, flowables, from the iterable factory method, giving it the list of URLs. We then say run this in parallel using the common fork join pool. And then what we're going to do is, for all the things that are now running in parallel, because we have a parallel flowable, we're now going to go ahead and apply the download and store image function. And that will do all this processing in parallel. And then when we're done, we have .sequential, which is going to merge all the values back from this parallel flow into a single flowable. So we end up with a flowable to one flowable of sequential processing. Then we go ahead and collect that into an array list. And then we go ahead and print that result out using, in this case, blocking subscribe. So that's probably a little bit cleaner. I think it's quite a bit cleaner than writing this code. But it still, in my mind, is not quite as clean as parallel streams. Parallel streams are just so concise and so easy to tweak and switch back and forth from sequential to parallel. Whereas the RxJava stuff is just a little bit more convoluted. And I think, to be fair to RxJava, it's not really meant to be a parallel processing engine in quite the same way that parallel streams is meant to be a parallel processing engine. RxJava is really intended more for asynchronous reactive programming, and it has all kinds of features built for that. You can use it for parallel processing, but that's not really its design center, per se. So I just wanted to go back and kind of talk about this solution. This is now more comprehensive. I have gone ahead and pushed this to my GitHub repository. So if you go back to the GitHub repository, you will get that new version. So let me go ahead and reshare my browser for a second. So if you were to come over and go to my GitHub website, you would see the elements here. I've got EX2, which is the version we just looked at that does the downloading of the images, comparing parallel streams with different variants of RxJava. We have EX3, and that's the one that basically reads the feed from the emitter of prime number candidates and checks to see if they're prime or not. And then there's something else here which I haven't really done a lot with yet, which is the EX1, which don't look at yet. It's just a bunch of placeholders for things I'm playing around with. So that basically wraps up what I wanted to cover today. I hope you have a better understanding of RxJava. I'm continuing to have fun playing around with it, and I'll probably add some more features or come up with some new examples to show in future lessons. If you go back to my YouTube channel and we look at the community tab, people have been voting on what else they would like to see. So far we've looked at a couple of RxJava examples. We've looked at a Completable Futures example. And I think what we'll do next perhaps was we'll take a look at a more interesting parallel streams example. So that's probably what we'll do tomorrow. We'll look at parallel streams. The cool thing about the example that we'll look at tomorrow is they're both parallel streams variants of it as well as Completable Futures variants of it. And at some point, I'll also create an RxJava variant of this as well. So we'll really be able to do kind of a Rosetta Stone, apples to apples comparison and contrast with these different mechanisms, which is kind of fun. So the goal of all this, of course, is to help people get a better understanding of how these different frameworks work. And then speaking of which, you might want to take a look at Venkat Subramanian, who is a really interesting guy. He's given tons of videos. I love to watch his stuff. He's not only is he a real knowledgeable expert on all things Java and RxJava, he's also just a really hilarious speaker as well. And he has a nice tutorial, it's a couple-hour tutorial actually, called Java Streams versus Reactive Streams. And he goes through and he really looks very carefully at Java streams, Java parallel streams, RxJava. I think he also actually looks at Completable Futures and kind of compares and contrasts them across a number of different dimensions. And that's very useful as well. I've got a lot out of that discussion. So I'll eventually work some of those things into my other tutorials that I give. But right now, I really just want to focus on the code. And so we're not talking as much about concepts. But hopefully, you're learning something interesting from this discussion. So please continue to join and ask questions. Oh, there's another question. The question is about the asynchronous completion token pattern. And let me take a look here. So if you go over here and you Google asynchronous, completion token pattern. This is a pattern I wrote years ago. Gosh, it's been over 20 years ago, almost 23 or 4 years ago. And you can find a bunch of videos that I've given talking about this. There's an interesting one here, which talks about the application of the asynchronous completion token pattern for C++. If you go here, you should probably find the asynchronous completion token pattern that I wrote years ago. Let's go see if we can find my actual paper. And let's see, here it is. Oh, even better. Let's go look here. Let's say, I know what the link is. It's this link. So this is a paper I wrote many years ago. It appeared in the POSA 2 book, the Pattern-Oriented Software Architecture Volume 2 book. And it talks about how you can write totally asynchronous programs, which have maybe just one thread, and be able to associate two-way calls with the one thread that you've got. And so essentially the idea here, and if you read the example, it'll talk through it in some detail. What you do is you create an asynchronous completion token, or an ACT, which is sometimes known as a magic cookie, and you pass this with every request. And let's see, here's kind of the idea. So a client makes a request, and keep in mind the client either here could be a pure client, or it could be an intermediate server which serves as a client to other servers. So for example, in a modern microservices architecture, you've got pure clients, which might be web browsers or mobile devices. They talk to intermediate servers, which are then clients for other back-end servers. And so the kind of the front-end server or the intermediate server is both a client and a server. It's a server to the ultimate client, but it's a client to the other servers. And what you want to do is you want to be able to have the intermediate servers send out requests to be able to get responses back, say in a microservice architecture, but you don't want the intermediate service to have to block. You don't want the intermediate server to have to block waiting for those responses to come back. And so the way you do it is you pass what's called an asynchronous completion token, which is typically a magic cookie or some kind of number that's generated or some kind of value that's generated, and you insert that with each request. And then you can return right away. There only needs to be one thread of control or a pool of threads. There's no blocking taking place in the intermediate server at all. And when the ultimate server gets the request, it does the work and it sends the result back. And as you can see here, it passes the asynchronous completion token back to the client, which could be the intermediate server. So think of it like a cookie that you might have. And so when the intermediate server gets that response back, it uses the asynchronous completion token to go look up the state associated with that particular request. And that state could be stored in memory, it could be stored in a database, it could be stored in a file, doesn't really matter. And so once the intermediate server's gotten all the responses back from its ultimate servers, it then goes ahead and it can send a response back to the client. And that way you don't have to know anything about you don't have to block at all, which is the whole point of this. So if you read this paper, it'll explain the concept. The concept that is given here is in the context of an asynchronous client that you don't want blocking for results to come back. But the same concept applies pretty much as is with an intermediate server. And so that's how you can go ahead and avoid having to have threads that just sit there and block. The question is, does this pattern require bidirectional communication? This pattern really could care less about the directionality of the communication. You can have bidirectional communication. In other words, you could have a socket where you have a request and a response coming back over the same socket, like you would if you were a kind of a classic web browser. But it doesn't matter. You could have two one-way sockets or two one-way communication flows. They don't even have to be sockets. They could be message queues or whatever. And so it doesn't really matter. It could be one way, it could be two-way. All you know is that as a intermediate server, you create the asynchronous completion token, you associate it with some data structure or some record in a database on the intermediate server side. You send it off to all the different servers. They do their thing. They communicate back however they communicate back. And when you get the result back, you match up the request with the response. If you've ever done examples, if you ever send a FedEx package or any kind of guaranteed delivery package, then you would know that you can put a little kind of return address information in the FedEx air bill, and that will then be sent back to you when the package is delivered, so you know which package it was delivered from. And are there Java examples with completable futures? Again, this is sort of the way that things are done under the hood with completable futures. If you were to look at the completable future implementation, you would see that they pass around completion tokens that they use to get back. So a future is one example of a completion token, and you can do all kinds of interesting things with that. Okay, so I think that's probably it for today. Hopefully you guys learned something. Thank you all so much for coming, and I will upload this video to my YouTube channel just as soon as I can. So thanks, guys, and I'll talk to you soon.